Understanding gates. We're now going to explore the XOR gate. XOR is an exclusive OR. Now, remember back in the previous topic where we talked about the OR gate. With the OR gate, all the states, any combination of the states, except for when both of the inputs are off, all the combinations will turn on the output. All right, so what makes XOR different? The states need to be different. And then it will do something. So think about it. If both states are on or both states are off, we are not going to do anything. The output will be off. However, if input 1 is on and input 2 is off, the states are no longer the same, correct? So therefore, we'll do something. Let's take a look at that. How are we going to accomplish this? I told you before it was important that you understood the other three gates, the NOT, AND, and OR gates. Now we're going to combine all three. Ready? We have our truth table again down in the bottom right-hand corner. So when input 1 is off, input 2 is off, the output is off. And we just got done saying, if the states are both the same, the output's going to be off. All right, well, let's look at our circuit. With this, we're just going to use the symbols instead of a relay logic. So let's walk through. Notice, switch is off, the light is off. When the switch is off, the power comes into it, but the power cannot flow out, correct? And notice how this is wired. It goes from the switch to the NOT gate. This little dot here means that this wire is connected to that wire. This arch means that it's jumping over that wire. They're not connected. So here, this switch is wired to two places. One to the NOT gate, and the second one is down here to the second AND gate. So you can see this is off. This is off. What does a NOT gate do? It inverts it, right? So therefore, this is off. That means this side will be on. And you can see that here with the red line. All right, so our AND gate, both of our AND gates have an input that's on. Both of them also have an input that's off. What does an AND gate need? It's in series, right? Think of the two switches on your wall, that weird wiring that I have in my one room. Both switches have to be in the same state, and then my light in the room comes on. That's what an AND gate is. Both have to be on for the line coming out of it to turn on. So therefore, in this case, we only have one of the inputs on coming into the AND gate, so therefore the output's not going to be on. All right, let's look at it in pseudocode. If input 1 XOR input 2, okay, what does that mean? Input 1 is in the false state right now, correct? What's the state of input 2? Right there. What's the state of it? False. False XOR false. False, false, false. That evaluates to false. So therefore, if false, this then is not going to fire. Okay. Let's do the next one. This time, switch 1 is on, switch 2 is off, and the light is on. Okay, so we can see on, off. They're not the same. And then we get an on condition. Let's take a look. When the switch is on, power comes in one side, what happens? It flows through to the other side, right? It's going to pass through. We've closed the circuit, just like the light switch on your wall. So now it's going to flow over here to the NOT gate. It's also going to flow down here to the AND gate. With power on the NOT gate, what's the other side? False. There's not going to be any power flowing through it because the NOT gate causes it to invert, flips the state. So therefore our AND gate has no power coming to it here. This switch is also off, correct? So therefore power is not going to flow through this line and it's not going to come into this AND. So I've got off, off. Okay, we don't need to think about that AND anymore. It doesn't have any power to it. Let's look at our other AND. We have power right here at that. It's coming from the first switch. All right, but I have power here on the second line coming in. So I have power and power, and that's going to turn on my AND gate. Why? Why do I have power here? Look at the switch. Switch is off. This line is off. It runs through an inverter, which is the NOT gate, and flips the state. Off, on. Okay? On and on into my AND gate means I'm going to get an output from it. I'm going to turn on that light. If the light were connected right here, it would turn it on. Instead, they're wired together. So I have an AND wired to an OR. What do we know about an OR gate? They're wired in parallel. So if I have a switch here and a switch here, this switch is on, the OR is going to turn on. And that's what we have here. So let's look at it in pseudocode. Ready? All right. What is the state of input 1? It's true. What is the state of input 2? It's false. Look at your truth table. True, false gives you true. There you go. So now you can say that this will evaluate to true. Therefore, the then is going to fire. That's going to turn on the light right there. Just makes sense to you. Stop. Make sure it makes sense. Don't move on. XORs confuse people. It even confuses people in code when they don't have to deal with this circuitry right here. So I'm hoping that you'll get an aha moment that you can see the difference between an OR and an XOR. There are times when you want this condition to occur. Let's carry on. All right, this time let's look at when switch 1 is 0, switch 2 is 1, and then we're going to get an output. Here it is. All that we did was just flip-flop this. We just switched it over. So therefore, we don't need to walk through all of this, right? It just took the circuits that were before and it just flipped them. Because now you can see the AND is on up here because this switch is on. This one is off because that switch is off. The OR is on, the light comes on. Here's our pseudocode. Here we go. Ready? Input 1, what's the state? False. Input 2, what's the state? True. What's that going to evaluate to? Look at your truth table if you don't know. A false and a true gives you a true. There you go. This will evaluate now. If this is true, yep, we're going to do the then. We're going to turn on the light. All right. Let's look at the last one. Now, if our switch 1 is on, our switch 2 is also on, this is that special condition that makes XOR different than OR. With an OR gate, this would be on. However, with an XOR, notice this is the only thing that's different. This is off. And this is where there are times when you want to know this. You want to know if both of these are on, I don't want that to come on. Here's the circuitry for it. So if I have them both turned on, of course I'm going to get power. These are connected directly to it. I'm going to get power there and I'm going to get power here. But my NOT gates are going to flip those states, aren't they? Uh-huh. So if that's on, what's that? Off. And needs them both to be on. So therefore these are turned off. Let's go through the pseudocode. What's the state of input 1? True. What's the state of input 2? True. Look at your truth table. It's going to be false. It's going to evaluate to false. Therefore, the then in the if-then statement is not going to fire. This is the symbol for XOR. Very similar to OR, except that it has a slash in the front of it. You can see it right here. See? More of a curve, really. Let's look at the takeaways. Exclusive OR, that's an XOR. If both input states are the same, then the circuit computes to false. Doesn't matter if both inputs are false or both inputs are true, they're the same. So it's going to compute to false. Else, the circuit's going to compute to true. That's it. Spend a little time, make sure you understand that.